Now let's try and look at the examiner's mind. If you're sitting this particular topic in an examination, I'm talking about angle between the radius vector and the tangent, and of course angle between curves. If you looked at the typical university problems, most of the problems focus on finding the angle between the two curves. And what skills you require is ability to differentiate. In fact, if you looked at our examples, all probable functions have been conceived, be it secant, cosecant, 1 by log, any other function that may be required depending on the past examination papers and also some of the questions we have added ourselves. So the differentiation must be perfectly mastered. If you are struggling with your basic differentiation skills, then this could be penalizing. If you don't end up getting a correct differentiation, your angle between curves can be completely wrong. And the skill to simplify and also to find the angle between curves calls for certain amount of trigonometry. In case of orthogonal curves, it becomes a very, very straightforward affair. If you calculate tan phi1 and phi2, if you take the product, if it is -1, then you are home. But otherwise, you may require certain amount of trigonometry, remembering some simple formulas such as tan inverse of x minus tan inverse y, or in some cases tan inverse x plus tan inverse y, as you saw through. And some of the difficulties that students assume are some of the difficulties that students actually face are the following. Sometimes people get lulled into the conclusion that they may have to remember the standard curves. They start by hearting the equation for chordioids, parabola, hyperbolas, which is actually not required. If you looked at 99% of the university papers, these curves are actually given. These are mentioned. Whether they are talking about cycloid, cardioid, hyperbola, parabola, they are all mentioned. But however, in summary, we have added, that is especially introduction to polar curves, we have added all possible curves with equations. If you want, you can visit that page and familiarize yourselves how those equations are got and how they are interpreted. That is very, very important. That can help you visualize what is what. Otherwise, in most of the university papers, the equations are mentioned. Remember, it is not always the angle between curves. Sometimes you may be asked to compute the slope. Then how would you do? You would actually be computing theta, you would actually be computing phi, and then the sum of them would give you the angle psi, and then tan psi would give you the slope, right? It is not always phi2 minus phi1, the angle between the curves. Sometimes it can be phi and sometimes it can be psi, which can also be calculated, but 90% of the occasions you are asked to compute the angle between curves. Okay, so that is very, very important. And also under this chapter, one derivation that you invariably get in most of the papers is establish a relationship between the radius vector and the tangent. That is, tan phi is equal to r d theta by dr. And we have also given the memory structure, how to go about this. That is, start with the standard derivative definition of the slope, then the coordinate geometry definition of the slope, then equate the two, eliminate the independent variable x, bring in the independent variable theta, and then simplify. Okay, that's very, very easy to recall that particular derivation. And many times, the numerical value of the angle between the curves is not expected. In some cases, you may end up getting that, but if you don't get the numerical value, do not panic. Sometimes, you may get in terms of E, sometimes you may get in terms of N, so do not panic, okay, if you do not get the numerical value. In some cases only you get the numerical value, but in 90% of the cases, you will get in terms of the parameters N, E, or whatever therein. So do not worry about it. And many times, it is easy to identify the orthogonal curves. For example, if you are looking at circles, if the circle is flipped by 90 degree, then what happens? The tangents drawn at the point of intersection are automatically perpendicular to each other. Now let me also give you example of two more curves, whether they could be orthogonal or not. So let's have a look at those curves now. Now let's see in what cases, under what circumstances the curves can intersect orthogonally. That's very important. The moment I say orthogonally, your job is 50% reduced. All that you got to do is find tan phi 1 into tan phi 2, and that is, if that is equal to -1, they are intersecting orthogonally. For example, you have two circles here. You can clearly see that one of the circles is represented as r is equal to a sine theta. A can be an arbitrary constant, and this is going to be r is equal to a cos theta, where a is an arbitrary constant. And you would appreciate that even if a and b were different, for example, if this were to be equal to b, then also the orthogonality condition is unaffected, because these arbitrary constants do not enter the problem. Because once you differentiate, take reciprocal and multiply by the original curve, a would simply go out of the picture. That's very important. So if it were a bigger circle and a smaller circle, don't worry, the condition of orthogonality continues to be satisfied, because this a in fact goes to determine the radius. Of course, this is the diameter, and therefore if it is smaller or bigger, it doesn't matter. Number one. Number two, observation. In this kind of situation, you can clearly see that sine of 90 plus theta would yield cos theta. And also, in the similar lines, if you were to have let's say secant square theta by 2 and cosecant square theta by 2, they are also orthogonal to each other. And remember that secant of 90 plus theta in general is minus cosecant theta. So therefore they are also going to be orthogonal. The only trick that you'll have to understand here is theta is multiplied by half, which is to nullify the power when it becomes multiplier when you differentiate this particular function. Very, very important. If theta were not to be multiplied by half, then the orthogonality condition could have been defied. So in such cases, finding orthogonality is very, very easy. Now we'll come to the chordioids. Somebody may think that if the chordioid is flipped, that is, this is the chordioid that pertains to 1 plus cos theta. And if the chordioid is flipped by 90 degree, that is symmetric about the y-axis, you would get 1 minus sine theta, which is not going to be orthogonal to this chordioid. Observe carefully. And what is going to be orthogonal to this chordioid would be 1 minus cos theta. That is, if I draw tangents at this particular point, it's going to be 90 degree. Whether you draw here or whether you draw here, in both the cases, the tangents invariably make an angle 90 degree. That is, the chordioid is flipped about the vertical axis. This is 1 plus cos theta and this is 1 minus cos theta. And what about the parabolas? Parabolas also, the same story goes on. That is, if you have parabola, one symmetric about the y-axis, one symmetric about x-axis, they are not going to be orthogonal to each other. For example, this is nothing but tan theta into secant theta, that's equal to r. And what about this parabola which is symmetric about the x-axis? This is of course symmetric about y-axis. That is, I am talking about a parabola which is symmetric about the y-axis. It comes like this. But if you are looking at the parabola, this parabola, that is of course given by r is equal to cosec theta multiplied by cot theta, right? So those are not going to be perpendicular to each other, but rather this parabola, when flipped about the y-axis, okay, the negative of that, those are going to be perpendicular to each other. And also one thing that you got to observe here, whether you draw tangents at this point, at both these points of intersection, it has to be by symmetry, common sense, they have to be orthogonal to each other, orthogonal to each other. That's very, very important. So we have given you some 4 or 5 examples. You can also yourself develop an intuition by looking at various curves, whether they intersect orthogonally or not. That's very, very important. If you are able to identify the orthogonality, the problem becomes absolutely easy for you. number one. Number two, it is very, very important that you go through the important aspects of this particular chapter under summary. One of them is the memory structure for deriving tan phi, which is fundamental to deriving angle between two curves. So understand that derivation in its entirety. How to remember that, that is also given. How you incept with the calculus definition of the slope, then coordinate geometry definition of slope, then equate those two. And instead of the independent variable x, you are going to bring in theta, and therefore you are able to get tan phi is equal to r into d theta by dr. So let me emphasize that. And also all curves, standard curves, you need not remember the equation. Of course, it is going to be given in the examination, but as a summary in the introductory chapter on polar curves, you would have every figure followed by its equation in polar coordinates. So that that would give you a complete visualization of what is going on the moment you confront the curve. And what are the best practices? How do you actually find the angle between the curves? How do you interpret the angle between the curves? That is very, very important, especially for this particular chapter. Even on differentiation, there are certain best practices. Because if you recall one of the problems where we took the reciprocal and then differentiated. And if the curves were of the exponential form, they took logarithm and differentiated. In each case, the penalty or the penalizing because of the long differentiation was done away with because of those tricks. Those also have to be effectively remembered. So our summary is going to effectively serve as a very, very detailed compendium for you. Even if you spend 10 or 15 minutes before going to examination, all your doubts are going to be clarified. Be it the formula, be it the derivation, be it the best practices, be it the interpretation of result. So therefore, that is very, very crucial for you. So wishing you good luck. We wind up this chapter and move on to the Pedal's equation next. Now, in a typical examination for any university, what is expected as far as the Pedal equation is concerned? One of the indispensable things is the derivation of the Pedal equation. So we gave you a very, very simple structure to remember. That is, start with P is equal to r sine phi, where P is the perpendicular distance from the point, that is the origin, to the pedal. Pedal is nothing but the tangent here. And therefore, all that you got to do to get the Pedal equation is express sine phi in terms of tan phi. And we gave you this formula. Please remember that is 1 by sine square phi is always equal to 1 plus 1 by tan square phi. If you remember this, Pedal equation is going to be a two-step affair because you are incepting with r is equal to r sine phi is equal to p, right? So therefore, the Pedal equation is going to be one-step affair. If you are able to remember this, so this becomes very, very easy. So this is one of the must for examination perspective. And the second thing is, you should remember both the forms of Pedal equation. That is, one is 1 by p square is equal to 1 by r square plus 1 by r power 4 and multiplied that by dr by d theta. Okay, whole square. Remember, many students make the error of writing it as d theta by dr, which is wrong. Always ensure that rr would be diagonally placed. And the second form that you got to remember is that you take 1 by r square outside and then you can recast this as tan square phi. That is the definition of angle between radius vector and tangent. So that way also you can place. And also you have to be familiar with trigonometric manipulations because sometimes you may require phi. For example, let me recall one of the examples that we did. So when we got cot 2 theta, or when we had a situation where we had to simplify and get to this particular situation. So in these two examples, I think I'm talking about example 4 and 5, you can see that we had to simplify to get the angle phi. That is, whatever function you get, express that in terms of tan and then reckon the value of tan. For example, minus cot 2 theta, assuming 2 theta to be acute, this could be rewritten as tan of pi by 2 plus 2 theta, right? So you can reckon the value of phi. This is very important. So along with the remembering of the Pedal equation, the derivation, your ability to simplify things trigonometrically is also very, very important. And when we simplified this, we needed the formula, what is tan of a plus b, that is tan a plus tan b divided by 1 minus tan a tan b. So that is also required. And third thing, basic differentiation. Whenever you have exponential form or whenever you had complex forms of differentiation, for example, one of the things that I want to emphasize here is when we had a e power theta divided by 1 plus theta whole square, the taking of log and then differentiating gave us a significant amount of labor reduction in differentiation. So those points had to be very well understood. And all problems are procedural in nature. That you'll have to understand, because we went through some 10-12 years of papers and we found that all problems on Pedal equation were procedural in nature. The only things that were given to test your competence was your ability to differentiate and simplify things. Okay, so that has to be borne in mind. And third thing is whether you are asked to find the value of p in a general case, or whether you are asked to derive the Pedal equation. Both are many times coincide, because if you are able to get a function tan phi as a function of tan itself, it easily reduces to p is equal to r sin phi. Do not get confused, because this is the inception point for Pedal equation. So therefore, in some cases, if tan phi, that is d theta by dr by 1 by r into r, in fact reduces, rather is a function of tan itself, the Pedal equation reduces to this. So don't be wondering why exactly it happens, because this is the inception point for deriving Pedal equation. So this is what the examiner looks for in summary: a correct derivation of Pedal equation, a perfect remembering of various forms of Pedal equation. Two forms we had to use in many problem solving. And third thing is your ability to differentiate efficiently, and then ability to simplify trigonometrically. So if you have these 4 skills, I think you can score out of out in this section. So therefore, let's move on and look at more discussions. Now, what kind of questions you may get under the topic of radius of curvature, what is expected of you by an examiner, is all that we are going to look at now. Now, one of the skills that you need to possess if you want to score out of out under this section is that you got to be quite good at differentiation and algebraic simplification. That's very important. And also, many times you may have to parameterize the equations to reduce the labor of differentiation and algebra. And also, if you parameterize the Cartesian equations, the final equations look pretty elegant, and it becomes very easier for you to plot if you are trying to use for a graphing application. But of course, that scope does not exist, because you are in a situation where you are writing your answers on the question answer paper. Now, these forms are very, very critical for you to remember. But what is very, very critical for you to remember are these 2 forms. In fact, we have emphasized that the parametric form could be easily arrived at by following the procedure. Here you need not remember the equation. In fact, if you looked at the discussions, we have made it very clear that the procedure for deriving equation, rather radius of curvature in the parametric form is quite easy. All that you got to remember is the Cartesian form of expression for radius of curvature. And of course, the Pedal form is hardly used in any of the examinations unless a specific problem is designed which relates to, say, orbital mechanics or something like that. But however, in order to derive the polar form, pedal form serves as an intermediate form. But till far, in most of the universities, the derivation of polar form is not asked for. But what is asked for is the problems using the polar form of polar form expression for radius of curvature. So that should be understood very, very clearly. And polar curves are quite easier to handle when compared to the Cartesian curves. And Cartesian curves require good amount of algebraic simplification. You need to be very, very cautious when you are differentiating. But whereas the polar curves are very easy to differentiate and easy to simplify also. And also, if you are trying to find the radius of curvature at specific points, you need to be switching the definition from dy by dx to dx by dy in case dy by dx is not defined, it is tending to infinity. So this is very, very important, and many times the examiners deliberately give you a situation where dy by dx is not defined, and you will have to define your first and second derivatives with respect to y instead of with respect to x. This is very, very important. And for you to visualize the nature of the curve is not at all important in the examination, but however, for your satisfaction, you can make a rough sketch of the curve so that you are able to visualize what exactly is going on. Especially if somebody asks you to calculate the center coordinates of the curvature at a given point for a curve, then the sketching of the situation may help, and especially these would belong to the typical conic sections, so therefore you don't have to worry about constructing complex curves. For example, it could be parabola, it could be an ellipse, so things are pretty straightforward in those situations. So these are some of the important expectations of the examiner. You are absolutely thorough with your basic differentiation. You are also quite good at algebraic simplifications, and finally you got to remember two important formulae, if not all. One is of course the Cartesian, one is of course the polar. Unless the derivation of polar form of radius of curvature expression is sought for, you don't have to worry about the pedal form of the radius of curvature. So the first two are very important. The parametric is simply the procedure that you would follow, because if you looked at so many of our previous discussion, first find dy by dx using the parameter t. That is what you are basically doing here, is you are finding dy by dt divided by dx by dt. And once you do, you in fact get an function which is in terms of t, and then once you seek the next derivative, that is when you are talking about d square y by dx square, then what happens is you are going to differentiate this, and also you are going to get dt by dx, which you have already found when you are constructing the dy by dx, that is reciprocal of dx by dt. That's going to be brought over here. So therefore once you find dy by dx, which is this, and d square y by dx square, constructing the radius of curvature is very simple, because you remember the Cartesian form. So Cartesian and polar form are invariably expected by the examiner for you to remember. So this is the gist of what you need to score out of out under the topic radius of curvature. So let's move on and look at more discussions.